Okay, so we were discussing on this code conversion techniques. So today we will first look into another code converter which will convert binary code to gray code. So gray code is a special type of code where the successive decimal values, so they differ by only one bit. So take an example here. Say we have we take this example. Okay, so say the value 0000. So in this column, so if we just write the corresponding decimal value, then for 0000, so the value is 0. So 1, 2, 3, 4. So it goes like this. Now you see that if you look into the binary pattern corresponding to successive decimal values, so 0 to 1, only one bit is changing, the LSB is changing, but when we are going from 1 to 2, so you see the two bits are changing, the LSB, B0 and B1, so both are flipping. Similarly, when we are going from 2 to 3, again only the LSB is flipping, but when we are going from 3 to 4 here, so here you see that 3 bits are flipping. Now, this actually sometimes not very much advisable, particularly when you have got applications in communication and all, where we want to we want that the successive values, so they should not flip many times. Also, when we have got some integrated circuit chips, VLSI chips, and we are a set of signal lines are running with the signal lines in successive time instances, so it will assume successive decimal values. So it is expected that those values, those bits will not flip much from one value to the next value. This is particularly true when we look into say microprocessors where there is address bus, okay, connecting to memory. So address bus, it generates the successive addresses, and then if I am following binary pattern, then there will be a large number of bit flips. So this leads to a good amount of power consumption, bus power consumption. So what we do, we convert them into something called a gray code. So in a gray code that is shown here, so in the right side, so here this, if you look into the value from 0 to 1, only the LSB is flipping, from 1 to 2 only the bit G1 is flipping. So bit G0 continues to be 1. Similarly, from 2 to 3 only bit G0 is flipping, other bits remain unaltered. So in this way, if you look into any two successive bit patterns, successive decimal values, their gray codes, they differ only by one position, only one bit will be flipping, so others will remain unaltered. So we define something called Hamming distance. So Hamming distance between two patterns, say x and y, is equal to the number of bit changes from x to y. So this is defined as the number of bit changes between x and y. So in case of in case of binary number system, so you see that it is not a fixed value. So many, sometimes only one bit flips, sometimes, particularly if you look into this 7 to 8, this flipping, you see that all the 4 bits are flipping. So there the Hamming distance becomes high. On the other hand, if you look into the gray code pattern from 7 to 8 also, you see only this bit is flipping, others are not flipping. So in case of Hamming, in case of gray code, this Hamming distance is always equal to 1 between two successive decimal values. So this has got many application in digital systems, and so this code conversion is this decimal to binary to gray code conversion is sometimes very useful. So the way it is done, so this is the logic. So it is the MSB is copied directly. So from this MSB, so it is XORed with the next bit to produce the next one, produce the next most significant bit, and again, so this binary code. So this is the binary code that we are trying to convert into gray code. Okay, the 5-bit binary code we are trying to convert into gray code. So this binary digits, they are XORed to get the next code. So we will come to this definition via this truth table. So we will start with the truth table here, and then we will show you that this actually leads to this functionality. So let us take this simplification of this code. So, if we look into the corresponding Carnot maps for G3, G2, G1 and G0, that is G3 is this column, G2 is this column. So, if you look into the corresponding Carnot maps, so G3 is 1 from whenever B3 is equal to 1. So, whenever B3 is equal to 1, G3 is equal to 1. So, here you see in the Carnot map we have done it like this, and if you do a grouping and do a minimization, then the equation that we get is G3 equal to B3. Similarly, for G2 the function turns out to be B3 bar B2 plus B3 B2 bar. So, which is nothing but B3 XOR B2. Similarly, G1 gives me B2 XOR B1 and G0 gives B1 XOR B0. So, this is as per the definition that we have here. You see that here also the basic definition of gray code is like that, and you see that the corresponding Boolean function. So, that is also leading to the same thing. So, you can very easily draw a logic diagram which can convert a 4-bit binary code into gray code, where this B3 will be directly copied to G3 as per this equation, G3 equal to B3, G2 equal to B3 XOR B2. So, G3 for getting G2, so B3 and B2 they are XORed, so get G1, G2. Similarly, G1 is B1 XOR B2, so this is XORed here, and G0 is B0 XOR B1. So, that gives the LSB. So, this way you can have a very simple gray code converter using XOR gates. Next, we consider the other way, that is starting with the gray code, how can we reach the binary code. So, this is the standard code conversion that we have. So, if we say that okay, this is the these are the decimal values. So, if we say that here I am writing down the decimal, then this is 0, 1, 2, 3, 4, 5, etc. Now, here also these values are known. For gray code the values are like this, for binary code the values are like this. Now, the way it is done is this MSB will be directly copied, and then so this is the this is the gray code that I have 10100. Now, that is 1 is copied directly to the binary MSB. So, that 1 is copied, then this bit is XORed with the next gray coded bit 0 to produce the next bit. So, this way it goes. So, this binary code produced, binary bit produced, so that is XORed with the next gray code bit to produce the next binary bit. Okay. So, that is the logic. So, we will see that this really happens if we are looking into the truth table. So, let us see that okay, this is the truth table. So, for the function, so B3 equal to G3, B2 becomes equal to G3 bar G2 plus G3 G2 bar. So, B3 is B2 is G3 XOR G2. Similarly, B1 becomes G1 XOR B2. Okay. So, this way we can get the individual bits, and this B0. So, B0 is a big expression like this, and then you can simplify, and finally, it boils down to this B0 is G0 XOR B1. So, this actually this B1 is given by G1 XOR B2 and B2 is given by G3 XOR B2. So, if I just expand it, so this is so this can be so in the previous step at this point, if you see, so B1 turns out to be G1 XOR G3 XOR G2. Now, in the next one, you see that we have got this G1 XOR G2 XOR G3. So, that part we can simplify to have G1 B1 directly. So, here this the logic diagram of this binary to the gray to binary code converter is something like this. We have got this G0, G1, G2 and G3 on the left side. So, G3 is directly copied to B3, and this G3 and G2 are XORed to get B2. Now, for getting B1 I need to XOR G1, G2 and G3. So, that will require a 3 input XOR gate. So, to simplify, so G2 XOR G3 has already been computed in B2. So, this B2 is taken here, and we do G1 XOR B2 to get B1. Similarly, for G0 I need G0 for getting B0 I need to XOR all these G0, G1, G2, G3. So, what we do, B1 is already having G1 XOR G2 XOR G3. So, that is XORed with G0 to get B0. So, this is possible because XOR is a linear function that we have seen, and so it is associative in nature. So, you can do any XOR at any you can do the XORs in either order. So, that way it is giving us the flexibility. So, you can do this for this gray code to binary code conversion. So, we can convert binary number 0 1 0 1 to gray code like this. So, this is 0 1 0 1, this is the binary number. Now, for the gray, so this is the circuit for gray code converter. So, 0 will be copied here, then this 0 and 1 are XOR to get 1, then this 0 and 1 are XOR to get 1. So, this way it goes. So, final solution it becomes, so 1 0 1 0, it is when it is converted to gray code, it is 1 1 0 0. Or if we want to convert the gray code number 1011 into binary, so this gray code bit is 1011. So, this this 1 is directly copied here, then the MSB is directly copied, then this MSB and this bit G2. So, they are XORed to get the bit B2, then B2 XOR G1. So, that gives me B1. So, that way it goes. So, this is the pattern that I get is 1 1 0 1. Next, we will look into another code which is known as BCD to XS3 code. So, many times what happens is that we want to add some base to the code. So, we do not allow some of the codes to appear. For example, here, so XS3 code means whatever be the value, from there you need to subtract 3 to get the actual value. For example, so if I look into this pattern, you see that here the value that I am getting is 3. If I just take it the binary representation, so this is 3. So, XS3 means from this I need to subtract 3. So, if I 3 minus 3 is 0. So, this actually the corresponding decimal value is 0. Similarly, so this is 0 1 0 0, that is 4. So, to get the actual decimal value I have to do 4 minus 3, that is 1. Similarly, 1 0 1, so this is 5. So, 5 minus 3 2. So, XS3 code means, so it has got an excess of 3 from the value. So, if I am talking about BCD to XS3 conversion, then so BCD can go up to the digit 9. So, it is going from 0 to 9. So, this is my 0 and we have 9 here 1 0 0 1. So, up to this much. So, 9 will be converted to 12. Okay. So, that in the 9 plus 3 12. So, this is the XS3 representation of 9. For rest of the bit pattern, 4-bit pattern, I do not need to consider, because in BCD we do not have these combinations 1 0 1 0 1 0 1 1 and all. So, for them I can take the output to be simply do not care, because they will not appear in the conversion process. Okay. So, these patterns will never come. So, with this we can we can go to the circuit for getting the converter BCD to XS3 converter. So, it is like this, that we have this say so the first the Z bit. So, Z so X, Y, Z and W. So, this Z is the first one. So, Z is this LSB. So, corresponding to that, if you look into the circuit, so it becomes Z equal to D bar or D dash. Similarly, Y, so this column, so this will give us CD plus C bar D bar. So, this is the XNOR function. Then this part X, so this X, so this gives us the function B bar C plus B bar D plus B C bar D bar, and then for W we get A plus B C plus B D. So, I can design a logic circuit for this W, X, Y and Z and get this BCD to XS3 conversion. So, after manipulation of these Boolean expressions using these common gates for 2 or more outputs, logic expressions are given by this. So, this is this Y is CD plus C bar D bar, that is one NOR gate. So, we can CD plus C bar D bar is an XOR gate. So, XNOR gate. So, this is actually though written as plus, but this is actually one XNOR function. So, this is the XNOR function. Similarly, here, so B bar C plus B bar D plus B C bar D bar. So, this is XNOR function, and then so this B bar common, so it is C plus D plus B bar C. So, the C plus D is an OR gate, and then with that we can take in AND with B bar. Then A plus B C plus B D, so we can take B common and C plus D comes as a common function. So, this C plus D can be taken as this C plus D can be taken as the common function for doing the manipulation, and then we can realize the circuit. Okay. So, this is the function, okay, so for x, y, z and w, and in fact, in this case this XNOR gate and NOR gate, so they are becoming similar. So, we can use this y. So, instead of doing XNOR, so we can do NOR also. So, that will also give us the similar result because of the presence of don't cares.